Hi everyone, in this video I'm going to run through the solution to the first Warwick Statistics Puzzle. So let's start by having a look at it. So we have n fair coins and we flip all of those and we remove any of those that land tails up. So we only have the ones left that were heads. We then take all of those heads and we flip those coins once more and count how many heads we have after that second toss. And we want to know what is the distribution of the number of heads we get after that second toss. So if you haven't had a chance to have a go at the problem yet, now's a good time. Otherwise, we're going to have a look at the solution to this. So first, let's just have a look at the problem in a bit more detail. So first, mathematically, what is the problem saying? So we have this random variable x1, which represents the number of heads we have after the first toss. So in other words, how many coins are still remaining after that first toss. And we can model this as a binomial distribution with the n coins we start with and a probability of 1/2 of getting a head. And so from this we can define x2, which is the number of heads we have after the second toss. And we know what the distribution of this is, conditional on x1. So x1 is the number of coins we have left after the first round, and so x2 will be binomial starting from this number of coins rather than starting from n. We start from x1 coins. And again, we have a probability 1/2 because they're fair coins of getting a head for each of these. So this is the conditional distribution of x2. What we want to know is the overall marginal distribution of x2, so independent of x1. And so we can also visualize this process graphically. We start off with all of our coins here. Here I have n being 10. And we start by marking off which of the coins landed tails after the first toss. So in this case, 4 of them got removed and we were left with 6 coins. So here, x1 would be 6. We then toss these remaining 6 coins and see which of those came up tails. Here we have an orange cross to mark a tail. And then we see how many of those are left. So we have 3 heads left after the second toss. And we want to know what is the distribution of the number of heads we have left after this whole process finishes if we were to repeat it multiple times. And so there's perhaps a more elegant way of looking at this problem, which leads to quite a simple solution to it. And the trick is, rather than removing all of the coins, or removing the coins that came up tails after the first toss, we keep them in and just mark them as being removed. So, just as before, we start off with 10 coins, and we mark which ones come up tails on the first try. So we now have 6 heads remaining, but rather than just flipping those, we flip all of the coins again. And we mark them with an orange cross if it came up tails on the second time. So if we had a heads on the first time, this is exactly the same process as we did before. We either get an orange cross and it's out, or we get no cross and it comes up heads, and we would count that. The only difference is when we got a tail on the first time and a tail on the second time. In this case, we'd mark it with 2 crosses. But this doesn't really matter. If it has a cross at all, it's been removed at some point, and so we can ignore it. So this leads us to ask, how many coins do we have at the end with no crosses? We want to know the distribution of that. That would be the distribution of the number of heads we have left at the end. Because if we got a cross at any point, it would have been removed. And what makes this nice is because our tosses were all independent, the first round and the second round, the probability of having no cross is going to be the probability of having no purple cross times by no orange cross. Because they're independent, we can just times these together. And each of these for a single coin has a probability 1/2 because it's a fair coin. And so the probability of having no cross at all is going to be 1/4. We then have this for the n coins, and so the number, or the distribution of the number of heads we have at the end, that is the ones with no crosses, is going to be binomial n and 1/4. So this is the answer to the problem that we were looking at. And in fact, we can generalize this further. If we start off x1 coming from binomial with a certain probability p1, this could be 1/2 if they're fair, could be 1/3 if they're biased, and then we repeat this multiple times, so m times, each time drawing the next x from the previous number of heads with their own probability, could be 1/2, 1/4, whatever, then the final the final number of heads we will have a binomial distribution, that is n, and the product of all those probabilities for each round. So it's quite a general result. We can use a similar idea to this to prove that, or if you want to do this formally, kind of have a rigorous mathematical proof, I have a link here to my blog which discusses it on this post. So what other ways could we use to tackle this problem? Well, another way would be simulation. So we could do this either by using coding, Python or R or any other language, or just by simulating it in real life by flipping some coins. Now, to make this work, we'll have to make a bit of an assumption or a guess that the answer is going to be a binomial distribution. And then we can figure out using the simulations what the probability for that distribution is going to be. And this might seem like a bit of a leap, but I guess you could run these simulations and plot the curve and see that it looks reasonably binomial, and it wouldn't be crazy to believe that it would stay in that family. And so here's some code to do this. We repeat the experiment multiple times, 1,000,000 here. I just picked n being 100, and a probability of 1/2 because they're fair coins. And we use a random seed just to make sure that our experiment is reproducible. We have a function to generate binomial samples, and then we just run the experiment multiple times. So x1 comes from np, and x2 uses x1 as the number of coins, and then we use probability p again. And then we can divide this x2 by n to get an estimate for the probability for our binomial distribution. And if we add these all onto a list of p's and then average them out in the end, we get 0.2499. So basically a quarter there, as we would expect. So we'll now have a quick run through of the bonus problem. And in this, we start with 1,600 coins. And we repeat the process above. We keep doing it until we run out of coins. And we want to know, to the nearest integer, how many rounds do we expect to have to do before we run out of coins. So if we start off with 10, we might flip them and we get rid of 3 tails, we now have 7. We do this again, we now have maybe 2 tails gone, so we have 5, we then maybe lose 3 more, we have 2. We keep doing this until we have no coins left. I want to know on average, how long will that take? So there are a few ways we could do this. We could simply simulate it a load of times and see what the probability comes out to be. You could also use, you can model this as a Markov chain and use kind of standard Markov chain methods to figure out what the average hitting time of 0 is going to be. But there's actually a way of doing this kind of more mathematically. And it uses the same idea as before, that rather than discarding the coins, we just mark them as being removed. So we start, let's say here with 5 coins. And every time we get a tail, we kind of mark it as removed and just kind of let it still sit in the population, but kind of as a ghost. And we keep doing this every round here until all of them have been removed. So in this final round here, this is when the last coin was removed. And so we can write this out mathematically. So we have the same binomials, and then xi is binomial based on the last one. And then we can define this stopping time tau to be the infimum, so the first time that xk becomes 0. And we want to know this expectation of tau. So this is the very standard kind of Markov chain or stochastic process view of the problem, but it's not the easiest to work with. I didn't find that a solution came out quite easily. So instead, we can look at each coin individually, like we did in the previous solution. And so we notice that we can model the time until each coin gets removed as a geometric random variable. So if you're not familiar with a geometric random variable, it models, you can use it to model the number of times you can flip a coin before getting a certain outcome. So here's the number of times we flip a coin until we get a tail. Maybe this should be 1 minus p here if we're waiting for a tail to occur, but since p is a half here, it doesn't matter. So we can model each j from 1 to n. We have a yj, which are independent. It's the distribution of the length of time until that's going to give us a tail. And then we can define m to be the maximum of all of these. And m is going to be how many rounds we have. because as long as there's still one of these that hasn't hit 0 yet, or hasn't come up tails yet, then we're still going to be going around m. And what we want to know is the expectation of this random variable m. In fact, m and tau are the same random variable here, just a different name. And so this problem now boils down to finding the expectation of the maximum of a load of independent geometric distributions, or geometric random variables. And we can do this fairly straightforwardly. So we want to calculate the expectation of this maximum here. And it's a fairly common result that we can write the expectation of a random variable on the positive integers, or on at least the non-negative integers, as these tail probabilities. So the probability that m is bigger than k. The way to think about this is that if we were to calculate this expectation, we would be summing up the probability m equals k times k. And if k is 10, then it's going to appear 10 times in this sum for 0, 1, 2, 3, up to 9. So this is kind of equivalent to that. We can then say that's 1 minus the probability that m is less than or equal to k. And because all these y's are independent, we can say the maximum being less than k is the same as each one is less than k n times. So we just take this to the power of n. And we know what this is for a geometric distribution. You can just calculate this yourself or find it on Wikipedia. It's 1 minus q to the k, where q is 1 minus p. And so we have this representation of the expectation of m here. Now, unfortunately, this doesn't have a closed form. We can get a nice approximation to it by thinking of it as a Riemann sum. And so, yeah, we kind of view this as an approximation to these two integrals. And if you use the left or the right-hand sums, we either get just the integral of the continuous version, or 1 plus that if we just start it a bit earlier. And so we can bound this expectation, I shouldn't call this en, this is expectation of m, by these two numbers here. And so all we have to do now is compute this integral. And if we use the substitution u equals 1 minus q to the x, this comes out quite nicely. We do the substitution, we get this 1 minus u to the n over 1 minus u. And if you know the factorization of 1 minus u to the n, you'll know that this division comes out to be here. I guess if you take the 1 minus u and times it here, you'll see they all cancel out to get the 1 minus u to the n. And these are all very easy to integrate. We're going to get a 1 here, a half here, a third, a fourth, etc., all the way up to 1 over n, which is simply the nth harmonic number. So a harmonic number being the sum of the reciprocals of the first n natural numbers. And we also have this 1, or minus 1 over log of q. In our example, we have n is 1,600, p is a half. This integral comes to be 11.477 and some decimal places. So our expectation is between that and 1 plus that. So it's going to be between 11.477 and 12.477. And we only want this to the nearest integer, so it's pretty safe to say that it's going to be rounded to 12. I mean, you can maybe argue this isn't perfectly rigorous because it could be smaller than 11.5 and therefore would round to 11. But if you use the Euler-Maclaurin approximation, we can actually get some more rigorous bounds on this to make sure it does round to 12. So yeah, that's the solution to that. I'll be posting the next puzzle fairly soon, so look out for that, and hopefully people have enjoyed seeing the solution to this puzzle. Thank you.